Hello and welcome to the LUniverse virtual planetarium from Lancaster University. The following is a recording of one of our free live public shows that we ran during early 2021. I hope you enjoy. So today, and I'm sure you all know, we're going to be talking all about galaxies. Oh yes. Let's start our tour of galaxies and talking all about their importance by talking about what makes up a galaxy. Galaxies are a huge collection of stars, planets, gas clouds, dust, and dark matter, typically all orbiting around a central point, a supermassive black hole. Before we dive into the specifics of all these objects, let's use our own galaxy as a reference. Now, on an incredibly dark and clear night, you'll be able to see our galaxy as a milky smudge running across the night sky. The Milky Way, of course, is home to the Earth, the Sun, the solar system, and pretty much every single object you can see in the night sky. Light from distant stars and other deep sky objects get dimmer as it travels through space, in a similar way to how someone turning on a light bulb 3 miles away is a little too dim to see. This means the majority of things that you can see with your eyes and anything that we'll experience come from within our own galaxy. And actually, up until the end of the 19th century, scientists thought the galaxy was the whole universe and that nothing could possibly exist outside of it. So let's take a little look at what's included in our galactic neighborhood. Firstly, and probably most unsurprisingly, of course, are stars. Billions of them. Estimates as to how many stars exist in our own galaxy vary wildly, from 100,000 million to approximately 1,000 billion. But each one shares at least some similarity to our sun. They can be smaller or larger, older or younger, but they all work in the exact same way, fusing light elements into heavier elements, all starting with hydrogen into helium, which is what our sun is doing right now. Some of the biggest stars can fuse much heavier elements, working its way along a periodic table all the way up to iron. And stars can die in a myriad of ways and create things such as planetary nebulas and supernovas, with white dwarfs and neutron stars left behind. And all of these things can be found as parts of a galaxy. But stars don't typically exist on their little lonesome. They can be found in clusters, either open or closed. And as we've mentioned a few of these before in the series, I won't spend too long on it, but for those that haven't heard me prattle on already, a cluster of stars like M13 just here are simply stars that are bound together by gravity. This is an example of a globular cluster, which is fairly quite tightly bound together by gravity. The stars in it are quite old, and they're fairly stable objects. You might actually reasonably wonder, what's the difference between this, a globular cluster, and a galaxy, right? They're just collections of stars. Well, one of the main distinctions between a collection of stars and a galaxy is actually the existence of dark matter, which I promise we will talk about a little bit later, just not yet. Galaxies are also home to incredibly beautiful nebulae, up to you, which are giant clouds of gas and dust. So the one we're about to look at here is called the Omega Nebula, or M17, which is roughly 15 light years across, which is about 10 times larger than our solar system if you include the most distant objects in the solar system, so the Oort cloud. Nebulas are the birthplace of stars and planets, as bundles of gas and dust slowly collapse under their own gravity. Although they may look like really dense objects here, they're actually incredibly sparse. A nebula the entire size of the Earth, which is tiny of course, but a nebula the size of the Earth would only weigh a couple of kilograms. That is so remarkably low in comparison to the ton of air that is currently on top of you. Just for a little scale there. The last major component that galaxies possess are the ones that everybody gets incredibly excited about, and that is black holes. And here's one right now. Oh, lots to see here. Okay, in all honesty, I'm just being fairly difficult. The reason black holes, I love it too much. The reason black holes aren't actually black is actually really interesting. So when matter gets essentially brought in towards a black hole, it gets superheated through collisions and friction and other effects around the black hole. It gets superheated, become incredibly bright, and it become things called quasars, which make them actually quite easy to see as very bright jets. As I said, at the center of galaxies are supermassive black holes. And a supermassive black hole is fairly on the nose for what it actually is. It's a black hole of immense size, somewhere in the region between 1,000,000 to 1,000,000,000 times the mass of the sun. While we're certainly not equipped to comprehend such insanely large numbers, it is an impressive thing nonetheless. So again, that is a galaxy, and at the center there should be a supermassive black hole. Another quite logical question that I'm asked quite frequently is that if there is such a large black hole at the center of the galaxy, why aren't we all sucked into it? Well, that's because galaxies aren't space hoovers. They don't just suck things in. Black holes, very simply, are just large objects with lots of mass, so quite a large gravitational pull. So strong, in fact, that if you get close enough, light can't escape. But things can orbit a black hole in the same way that we orbit the sun and then don't get sucked in and fall into the sun. Gravity has the ability to pull things towards it, but typically isn't strong enough to do so. So whilst black holes, yes, have the ability to essentially destroy things, you have to get pretty close before that's a problem. So things are quite happy to orbit it from a fair distance. So with a bit of an idea of what galaxies tend to include, let's have a look at the different types of galaxies. We'll start with what you almost certainly picture in your head when somebody talks about galaxies, and that's the really famous one of a spiral galaxy. A spiral galaxy simply is classified by having spiral arms, which are the spirally bits. There are two main types of spiral galaxies, those with bars and those without bars. A bar is simply this straight bit in the middle. NGC 1300, the one we're looking at right here, is a barred spiral galaxy, as you can see by that barred stick in the middle there, and which the spiral arms then come out of. It's absolutely beautiful. A spiral galaxy is made up of three main parts. The bulge, which is the bit in the center, that typically contains old stars, those made at the earliest points in the universe, orbiting around the supermassive black hole in sort of a spherical motion. Outwards is the disk. So we've got the bulge, then we have the disk. The disk is the flat part, which contains the spiral arms and orbits around the center, a bit like our spinning record will turn. I mean, it doesn't actually turn like that, but it's a nice way to think about it. When I say the disk is flat, I am being fairly disingenuous. The thickness of the disk can extend up to 1,000 light years or more, which is easily 1,000 times larger than the solar system, and again, can be much bigger. Spirals are home to stars very similar to our sun, slightly younger stars full of heavier elements left over from previous supernovas. We exist in the outer spiral arm of the Milky Way as well, so this is about what we would expect to be used to. The final major part of a spiral galaxy is the halo, a sphere of objects that orbits the center. And this is where we can find things like nebulas or clusters of stars that we were talking about a little bit earlier on. The next type of galaxies are elliptical galaxies. If you think of a spiral galaxy as the new, exciting, star-forming regions of the universe, then galaxies are the old grumpy ones that don't do a lot. Unlike spirals, and maybe hinted at by its name, elliptical galaxies are, yeah, fairly elliptical in shape. They're basically like squashed spheres containing old stars and very, very little gas. These older stars and the relatively small amounts of gas means they are not star-forming regions. They're not forming that many new stars, meaning they're sort of the old graveyard-ish of the universe. We think that elliptical galaxies come from spiral galaxies merging together. These mergers can sometimes cause a flurry of new star creation, with all those gas floating around being able to combine and be a bit more dense, but then eventually things would settle down again and settle into these sort of states here. The stars in a elliptical galaxy don't all orbit in the same direction, roughly, like the ones in a spiral do. They sort of orbit in all sorts of different directions, which can be down to gravitational effects or interactions with other galaxies. Over time, all the gas in an elliptical will be used up, no new stars will form whatsoever, and eventually they will all die and the ellipticals will slowly dim and run out as well. Bit of a downer there. The final type of galaxy, and definitely the hardest to classify, are irregular galaxies. Another name, very creative from physicists, that helps you to remember what they are. They're irregular. It is testament to the sheer scale and diversity of the universe that there are so many different types of galaxies that we cannot put many of them into distinct categories. Irregulars do not have spiral arms, nor do they exist in elliptical shapes. Instead, they come in all manner of configurations. The origin of an irregular galaxy could be from a massive gravitational event, where some interaction has caused the mass movement of stars in a galaxy to change from a spiral or an elliptical galaxy into an irregular shape. Additionally, irregular galaxies can come because they're just very young galaxies. They're galaxies that haven't had the chance yet to form into spirals or form into ellipticals. Basically, time has not given it enough. There hasn't been enough time for the gas clouds to form into stars to then make up all the patterns that we see. Either way, irregular, spiral, or elliptical galaxies, they are all massive and very varied objects. And I think they're pretty cool. The existence of other galaxies is actually a fairly new phenomenon. Until the early 20th century, our Milky Way, as I said earlier, was thought to be the only galaxy in the universe. It was thought to be the entire universe. Then it became the only galaxy in the universe. But German philosopher Immanuel Kant first proposed the idea of island universes, similar structures to our galaxy existing elsewhere in the universe. But it wasn't until 1923 that Edwin Hubble managed to measure the size of the Andromeda galaxy, the one that we are looking at now, and managed to measure it as larger than our own Milky Way galaxy, thus proving that it had to exist outside of the galaxy, and therefore there must be other galaxies outside of the Milky Way. Hubble then went on to classify different types of galaxies, producing what is quite famously known as his tuning fork, which we'll go over now. This is actually still being used to this day to help us classify different types of galaxies. So on this fork, it's a very quite rubbish fork if you were trying to pick something up, more like skewers. Anyway, on this fork, you can see how different types of galaxies that we've mentioned so far get placed into different groups. Just above my head, sort of, is where we start with the ellipticals, and it's given a number based on how elliptical it is. So 0 is pretty spherical, and then the bigger the number, the more squished it is. From there, we split into two types of spiral galaxies, those with a bar and those without. So S or SB. The letter and then the letter next to it, so the A, B, and C, corresponds to how tightly wound and prominent the spirals are, with A being a very tightly wound galaxy with a very large central bulge, and C being far more loosely wound with a lot of the luminosity being spread out amongst the spirals, the bulge being a lot less prominent. Finally, the irregular galaxies are the ones that just don't fit on this system. So you might be wondering, why are galaxies defined in this way, using this weird tuning fork shape? Well, it's because Hubble believed this to be the order in which galaxies evolve and change over time. He said that galaxies start on the left as ellipticals and then flatten out into spirals over time. He called the ellipticals early type galaxies and the spirals late type galaxies, like so, which we'll definitely come back to in a second. And to the man's credit, you could definitely see where he's coming from. Okay, You can sort of see it, can't you? You can see how a sort of spherical galaxy looks like it sort of flattens out, and then as it starts to flatten, spirals can start forming, and then it looks like those ones, right? That is a perfectly reasonable way to interpret that. Some of you may have clocked on that I'm sort of implying that something could be a little bit wrong here. It turns out that galaxy evolution doesn't quite work like this. In fact, it's actually a lot closer to this. Oops. So yes, we believe that galaxy evolution is more likely to work the other way, that a galaxy will start more like a spiral, and then through interactions with other galaxies or galactic objects, the spirals can become ellipticals. Although I should really clarify, they don't follow a linear path. They don't start out as a big sort of really spirally galaxy and then get tighter and tighter and turn into a sphere. It's more likely they'll jump from one to the other. So some sort of interaction with a spiral galaxy will turn it into an elliptical galaxy. It won't just progress down that line. We know that the elliptical galaxies are the older ones, as we mentioned earlier, as they contain older stars, stars that formed right at the beginning of the universe and have lived until now. We know this because stars that were formed straight after the Big Bang can only be made of elements left over from the Big Bang, right? They can only be made of stuff that's floating around at the time, which is just hydrogen and helium. But stars that came a lot later could also include elements that are left over from supernovas and planetary nebulas, the deaths of other stars. So if we look at a star and it doesn't have a lot of elements that are from other dead stars, well, that means it must have existed before there were dead stars. So it must be really, really old, which we would call a metal poor star, a star that doesn't include a lot of metals. Elliptical galaxies are full of metal poor stars, really old stars. While spiral galaxies have a lot more metal-rich stars, so stars that are made out of lots of supernova remnants as well. So really, we think things are backwards. I should state there's technically nothing wrong, albeit now upside down, with Hubble's classification of different types of galaxies. It's not an evolutionary diagram. It does have some limitations. It's really hard to classify galaxies just by what they look like, because they can look different under different wavelengths, just like how you look different under X-rays than you do under visible light. And there's no reason that in space, the wavelength that we can see is the correct wavelength. All of them could be equally valid. And as I keep saying that physicists are fairly dreadful at naming things, here's why. These older galaxies, so as I said, the older galaxies of the ellipticals are still called early type galaxies. And the newer galaxies, which are spirals, are still called late type galaxies. Now, if you're finding that confusing, that's fine, because it is confusing and really stupid that it hasn't been switched back. It was a naming convention that was thought up incredibly early on and unfortunately has stuck. So if you ever hear early type galaxy, think elliptical and think it's actually old. And if you hear late type, that's a spiral and it's actually quite young. It's fine. We'll have to ignore it for now. Oh dear. Now, I'd be remiss if I didn't take the opportunity whilst talking about galaxies to show just how impressive our universe truly is. If we take a section of the sky that looks pretty much completely dark to our eyes and point an incredibly powerful telescope at it, we can see something truly remarkable. And that is what has been discovered over and over again by the Hubble Deep Field images. And this is where the Hubble Space Telescope stares at one point in space for an incredibly long time to collect the light from insanely distant galaxies to form images similar to this one. I showed this about 2 weeks ago, but there's no way I couldn't do it again. There are over 200 galaxies in this one tiny dark patch of the night sky alone, and each galaxy will house thousands of billions of stars. Each one is like to have a planet orbiting it as well. Not only is this an incredible thing to look at, but it's also a wonderful reminder that you can't just trust your eyes to see everything. And when we think we've understood the universe surprises us once again by an entirely dark patch of the sky being brimming with galaxies and life. Images like this can actually be really useful to explain the evolution of galaxies that we've just talked about. So those spirals turning into ellipticals, and potentially irregulars being the really early ones before they get a chance to form. But to talk about evolution properly, we're going to need to have a little chat about light and the speed of light, so please bear with me. Light travels at 67 million miles per hour in outer space, give or take. And when I say something is a light year away, I mean it's the distance that light travels in a year, which is about 6 trillion miles. So if something is 4 light years away, it means it takes light 4 years to get there. There's a 4-year delay between us sending light and, well, the object sending light and us receiving it. So the light we see from something that's 4 light years away is actually 4 years old. But that means when we look at an object that's 4 light years away, then the object looks like what it did 4 years ago, because the light we're seeing is 4 years old, meaning we're looking back in time. That idea is true no matter how far away something is. So light from a galaxy 100 million light years away has taken 100 million light years to get to us. There was 100 million year delay in the light being sent and us receiving it. The light we receive is 100 million years old, meaning the galaxy appears to us how it did 100 million years ago. It's 100 million years younger than it actually is. The galaxy sends the light that we can see, and then a million years later we actually receive it. And by the time we've received it, of course it's changed massively, but we won't notice that again until time has passed. The benefit of this, the massive benefit of this, is that we can see backwards in time. The further away something is, the longer light has had to travel, and so the further back in time we can see. With that in mind, distant objects look younger than they actually are. Again, we're seeing further backwards in time, which means we can actually see galaxy evolution in those brilliant deep sky field images that we saw before. If we were able to map galaxies into 3D space, we could effectively fly through a picture and see how the universe looked as we go back millions and millions of years. As we go deeper into space, you can see how we're now essentially looking backwards in time, again, because that light has taken ages to get to us. There is a delay. And as we continue to go back further and further and deeper into space, you can see how the morphology, the size and shapes of galaxies begins to change. As we start to go back, they become fewer and fewer spiral galaxies. Those lovely new galaxies, the new types, because they haven't been able to develop yet. We're going too far backwards. Eventually, we start to even lose the ellipticals. We're seeing more irregular shapes and patterns there. They're also a lot dimmer. That's partly through the way we observe them, but of course, they're going to be smaller objects in some cases. Lancaster University actually has experts that are working on these very distant galaxies, figuring out what the earliest parts of our universe actually look like. The effective time travel is an amazing consequence of a fixed speed of light. And if my explanation of this wasn't overly clear, I can only apologize. It is a very complicated topic, but an amazing one. And we can definitely go over it again at the end if people do wish to. Pretty cool. Pretty cool. But before we wrap things up, I did promise that we talk about dark matter. So the big question is, what is dark matter? Well, if I knew, I'd be pretty famous. I have a Nobel Prize and probably my own science talk show. I wish. Really, the answer is that nobody knows. No one has any actual idea what it really is. People have some good guesses. They've got some interesting statistics behind it, but no one knows. It is one of the biggest mysteries still remaining in physics, even though this substance makes up about 25% of the whole universe. Here's why it's difficult. Essentially, everything we can see, touch, interact with is all because of electromagnetic radiation. So light, photons, electrons. You can see me because information travels through electromagnetic waves to servers which interact via electrons, which sends more electrons to you, which then turns other electrons into light that become visible. The electromotive force is the reason we can see, why things emit heat, and why objects don't pass through each other. It's literally why you don't currently fall through the floor. You're effectively floating on a bed of electromagnetic forces. Don't think too hard about it. Dark matter, as you might have now just guessed, is very annoying because it doesn't interact with this force at all, meaning we can't see it. It doesn't collide with anything, meaning we can't put it in a container because it would literally just phase out of it. And it emits no radiation whatsoever. So no visible light, no heat, nothing. So what does it do? It interacts exclusively via gravity. Things can get pulled towards clumps of dark matter in the same way that we get attracted towards the sun and objects with large mass because of gravity. Here we go. Scientists figured out that the large-scale structures in the universe probably formed from these interactions with dark matter. Dark matter pulls regular matter towards it. If it can interact via gravity, which it can pull dark matter towards it, clumping it all together so that gas clouds can form. And those gas clouds can eventually then collapse under their own gravity to form into stars. In the early universe, it's predicted that dark matter would have been sort of spread out really far across the universe, with some parts more densely clustered dark matter than others, forming a web of highly dense and less dense dark matter regions. As such, matter would have been pulled along this web, slowly forming the universe. And I have a lovely video to show this. So the blue here is the dark matter. If we could see it, you can sort of see it in spirally webs, and the pinky, yellowy, nicey regions are regular matter that is getting pulled along this web. So dark matter forms into a cosmic web into regions of high density and low density, which then pulls regular matter together. That regular matter then gets compressed and can start forming galaxies, stars, clouds of dust under its own little bits of gravity as well. So dark matter pulls regular matter, and regular matter then makes up the universe. This means that our lives, our galaxy, our universe, everything we know and will ever exist, comes from the movement of matter that we can never and will never be able to see. And with that final note, that is our tour of galaxies. Thank you very much.
Make sure I'm unmuted first. Thank you for that, Andrew. So we've got a couple of questions in the chat. And first of all, Minnie A wanted to know, how do galaxies get their colours?
Oh, that's a really fun question. So the colours, okay, there's different parts to that. It's a great question, and it's made me I'm having to think now. That's always rubbish. So the colours come from a myriad of things. Firstly, when we look at really distant galaxies, we have to sort of make up the colours. I know that's a bit rubbish. By making up the colours, what we mean is that scientists get the images back in black and white, and they have to do some clever tricks, essentially, to get the colours to be visible. So if we take an image in the red, green, and blue spectrum, we can then combine the images to make colour, or we can look at some of the important features of an image to figure out what those colours should be. Now, different gases that float around in a galaxy interact with light in different ways. So some gases, when they get excited by light, by electrons, can emit certain colours of light. So essentially, some gas looks sort of bluey because when light interacts with that gas, it produces blue light. And some gas can look sort of green for the exact same reason. It's actually the same way technically the aurora works, is that it hits certain gases in the atmosphere and it produces light of that colour. Basically the same thing with the gas clouds. Different stars also have different colours based on their temperature. So blue stars are incredibly hot stars, really, really hot. And whilst the orange and red stars are actually, funnily enough, the cooler stars. It's basically the opposite way around to how taps work. That's a great question. Thank you so much.
Next up, how do you decide if something is a galaxy?
Oh, I can't wait for Brooke to be here next week because she is far more knowledgeable than I am. So as far as I am aware, and I will be told off if I am wrong, one of the key distinctions between a galaxy and not a galaxy is dark matter. It's its dark matter component. So as I mentioned earlier, you can get clusters of stars, and clusters of stars effectively, right, are very similar to a galaxy. They're stars, they sort of vaguely orbit-ish each other, but they don't have dark matter. A cluster of stars doesn't have a dark matter component, whilst a galaxy is full of dark matter. It's a lot of it, in fact. There's more that I could have gone into today about galaxy rotation curves that are all dependent upon large dark matter components, but we would have been here for another hour had I tried to do that. So I skipped that one for today, maybe another time. But yeah, galaxies need dark matter to be classified as a galaxy. Just thinking, how do we measure the dark matter if it's not there? We can't see it. Well, we can actually infer the gravitational interactions with it. So I said that dark matter interacts exclusively via gravity. So if we look at how things are orbiting, how things move, we can then figure out that there's some mass that's missing, right? If we can see that something's orbiting something that doesn't look like it's there, well, that must be some dark matter, right? There's a mass that we can't see, and that's how we figure out dark matter's there. And if there's not dark matter in in an area with lots of clouds of gas and dust and stars, that's a galaxy, I think.
So next is another question that Brooke will definitely have an answer for next week, but I'll ask you first. Do galaxies always form around a black hole, or does the black hole form after the galaxy?
That's such a good question. Absolutely saving that one for Brooke next week. Oh, this is evil. This is evil. I'm fairly confident. Emphasis on the word fairly. Oh, I don't. Jen, I'm really sorry. Although I have an idea of what might happen, I do not know. I can get back to you probably in a little bit with potentially an answer, but I can't answer that one just now. I don't want to say it and be wrong. So if you give me a moment, I will get back to you on that one.
Okay, so in the meantime, why don't galaxies just look like nebulas? Why do they have shapes at all?
Ah, that's a fab question. I think a lot of times it comes down to one of the worst things in physics. It's the conservation of angular momentum. So essentially, as things move through space, they have momentum. So we have mass times velocity. It has some inertial movement. It's what we actually call inertia. It's this idea that something has mass and it moves. Here we go. When things get tighter and sort of get brought down, they spin faster. A bit like how a ballerina, if they have their arms stretched, pulls them in, then they speed up. Ice skater, all the same thing. If you're spinning and you pull your arms in, you'll spin faster. That's the conservation of angular momentum. Effectively, what you see is that the easiest rotating shape is to, well, an energy efficient way to rotate is to flatten out across the, I think it's the plane of rotation would be the correct way to say it. So if I've got something that's rotating this way, so this ball's spinning like that, the plane of rotation could be here, and that's where things are going to naturally try and end up. So that's why you see quite a few spirals, because it's actually more energy efficient to be in that flat shape. So essentially it's because things in space have movement, gravity forces them into sort of orbital shapes, and it's actually the most efficient to be essentially orbiting on a central plane around the plane of the rotation, the orbit, which is why even in our solar system we have the sun, and most of the planets orbit at roughly the same height relative to the sun. We all orbit in the same plane, give or take, but we mostly do it because it is just more energy efficient that way for the universe to sort it out. That's why there is rotation like a spiral, and that's why there are some defined shapes. Basically, movement and gravity. Great question. Thanks.
So next up, what kind of interaction does a galaxy experience that can make a steep change in its evolution?
So, okay, that again, sorry.
Sorry. What kind of interaction does a galaxy experience that can make a steep change in its evolution?
Ooh, that's a great question. One of the main things that can take place is galaxy merger. So that's two galaxies smashing into each other. that would really change it quite drastically. For example, we're going to smash into Andromeda one day. Not tomorrow, in quite a long time. I think it's, oh, I used to know the number. It's either 4.5 billion years or 45 million. A big number. We are eventually going to collide into Andromeda, and that's going to change our morphology a lot. It's very likely at that point it would become an elliptical galaxy because of the gravitational interactions between things. Now, I want to point out, when galaxies collide, the stars aren't going to hit each other. Galaxies are mostly empty space, right? We understand there's a lot of gap between the sun and all our planets, and there's 4.2-ish light years between us and the next star. So there's huge gaps between us and other stars. So things will pass through each other, but they'll gravitationally interact, and that's how we can sort of get more like elliptical shapes. I hope that makes sense. So it's changes due to gravitational interactions with other things. For example, even a galaxy sort of doing a flyby of one of them can distort its rotation. It can distort the movement of stars within a galaxy as well. So yeah, gravity basically is the answer to a lot of these things. Back on the topic of what came first, it's like what came first, chicken or the egg, which came first, the black hole or the galaxy? We don't know, is what I've been duly informed. It's a topic of debate and research, a huge topic of debate and research, which ones comes first. There's an idea, like with a lot of things in space, that they formed roughly around the same time, which would make sense about how star evolution works. So a black hole is just a dead star. It's a star that has gone supernova, and then the neutron star that's left over is so massive that it collapses under its own gravity as well, and then forms a black hole. As that's happening, stars around the galaxy, well, around the area that will eventually become the galaxy, are also forming. So it's likely they could come at the same time. But of course, the jury is still out on that one, and it could go either way. Probably have time for one more, I think.
Okay, then. So last question will be, how far away are the furthest galaxies that we've seen so far, and what shape are they?
Oh, what's the furthest? I know that there is a lot of the lecturers here deal with these sort of galaxies. They are dealing with the most distant galaxies. We're talking a silly number of light years, hundreds of millions of light years. I think it's easily into the billions of light years away at this point. Well, redshift 7, which I would need someone to convert into distance for me / time. But I know that there's CR7, which is a galaxy that was discovered by one of our lecturers here, Dr. David Sobrow. That's at redshift 7, hence the name. And I just cannot for the life of me remember how you convert redshift into distance off the top of my head. Redshift is essentially a number we associate with how shifted light is, and light gets shifted further back in time because of the expansion of the universe. We're not touching that one today, but it is a way to measure it. So I think it is in the hundreds of millions, if not the billions of years. They look so varied, though. The problem is when we start to look this deep into space, we can't get a nice clear image anymore. The light from it is now so far away and so dim because of how it spreads out, a bit like a light from a torch again. Won't be visible over many miles. It spreads out, it's too fine. Light from these distant galaxies gets spread out over the universe, becomes very hard to see. As such, we don't get a nice clear image. We get a couple of pixels, or we get some effects that imply that there should be something there. But in terms of what they should look like, they could look so different. It could be irregular, as we mentioned earlier, some of the really early galaxies before they formed those spirals, before they formed into ellipticals. They could also be elliptical in shape. They could also be spiral in shape before they become an elliptical. The jury is definitely out on what they definitely look like, because, again, it's so hard to see something that old. Really fun question. And with that, I think... I've just had a fantastic little message from Pascal saying they've been talking about one which is at redshift 11, which is 0.4 billion years after the Big Bang. So that's really short, right? If you think the Big Bang is... 13 point something billion years old, years ago, sorry. So the universe about 13 point something, I think 13.4 billion years. If that's 0.4, that means we've seen galaxies potentially around 13 billion years ago. So that's 13 billion light years away. That's amazing. I love science when we get stuff like that come through. I don't do galaxies, but I love them. They're really interesting. I must say a big thank you to our moderators. First up, a big thank you to Pascal, who does, as she has done for many weeks now, fantastic question asking. Thank you so much, Pascal. And as well to Diego, who has been busy hiding behind the scenes. Go on, Diego. I can get you live. I'm going to do it myself. Hey, there we go. Fantastic.
Thank you for watching, and I hope you enjoyed learning a little more about our amazing universe. Our team from Lancaster University also runs shows for schools, community groups and more, both in person with our portable inflatable planetarium and online. But any in-person events are subject to current COVID restrictions. If you're a teacher, community group leader or part of a similar educational organisation, please do get in touch. We're particularly keen to make connections with those in our region of Lancashire and Cumbria, but we'd love to hear from you wherever you are. But for now, take care and keep learning more about the amazing wonders of our night sky. Thank you.